for games and information. Since so far we have covered week till week 11, so I'll be taking a recap till then. The last.
I think you're muted.
Oh, am I audible now?
Yes.
Yeah. Okay. Okay. So let's get started. This is going to be a recap till week 11, and week 12 will be taken on Tuesday. So that'll be it. So no further sessions after that. Okay. So let's get started. So some of you had asked me a few questions that you had some doubts in. So I'll take these questions when we get to that topic. So I'll quickly, briefly go through whatever we have discussed in all these weeks. Okay. Um, some of these questions, some of these questions were mostly just going through the details carefully, nothing more than that. Just pretty much algebra and not that. So I'll not be going through that part. But if you have any specific problem in any specific step, you can ask me that. The questions that were a little tricky, one of them that I felt was a bit tricky and needed proper discussion was question 2 from week 4. So I'll spend sufficient time on this one. But the others, I'll just skim through them. Okay? Alright, so I'll come to this question in a minute. Alright, so.
So like, what you say, maybe, so like whenever we do, let's say it's for week 3, so once we're done with week 3, then I can ask or something like that, whatever works for you.
Yeah, sure.
Oh.
So I'm starting with week 1. In week 1, what we talked about was what exactly is a game, what are the solution concepts for a game. The most standard one is a Nash equilibria, and there are a few ways of finding that for any particular game. So, one of those methods for finding a Nash equilibria is to look at dominant strategies or eliminate dominated strategies. For example, in this scenario, is there a dominant strategy here for any of the players? If there is, we can simply remove that and focus on the reduced game. So, to talk about, for example, dominant strategy, we basically should be comparing, for example, this with this. We can't have a clear comparison here, but this portion, this column 1, 2, 2 is always greater than 0, 1, 0, or even this one. So, these two can be eliminated. Reason being, R dominates L and M with respect to player 2. So player 2 will never play L or M as long as he has access to playing R. So that means this goes away, this goes away. Now, this having been eliminated, player 1 would also have an idea that player 2 will not play these two strategies, and hence he knows that he's just supposed to choose from these three, and hence he will choose T. So he'll remove these two. For him, the removal is just this much. That leaves us with 2 comma 1, which is TR. So what we get here is a Nash equilibria, but this is specifically a strongly dominant one. Okay, we can verify that this is one of the Nash equilibrias by actually looking at the matrix. So that way could be done by, let's say, going through the columns and the rows and noting down which it is. By the way, here we are assuming both are maximizing. So if we look at player 1, keeping player 2 strategy fixed as L, then player 1 would prefer playing C. If we fix player 2 strategy as M, player 1 would prefer playing T, and for the last one again, it would prefer playing T. On the other hand, for player 2, for each of them, he would prefer playing R. And that also leads us to the same answer, that this is the Nash equilibrium. So, using the method of this iterated elimination of strictly dominant strictly dominated strategy will lead you to finding the Nash equilibria of the original game. So what this means is, if you were to think of these two games as an original game and the reduced game meaning we have removed some strategies, or it's in some form, instead of looking at the whole game, we are looking at a part of it. So it depends what process is being used here, because process is not talked about in this first result. It says that if there is a Nash equilibria in the original game, and if that same strategy profile, whatever that strategy profile is, for example, if T comma R is available even in the reduced game, then this would be a Nash equilibria even in the reduced game. Meaning, if randomly I reduce it and say, so this is a random reduction without any logic or anything. Say I reduce it to, I want to keep T and R, and let me just keep L and C. So this becomes 1 comma 3, 2 comma 1, 3 comma 1, and 1 comma 2. Here again we can look for the Nash equilibria. That will be player 1, he would prefer playing C and T respectively for L and R, and player 2 would prefer playing R both the times. So this is still the Nash equilibria even in the reduced game. And notice here the reduction is without any logic. We just reduced it randomly. But as long as that strategy profile still exists in this new version, it would still be a equilibria. So that's what this first result says. Now, if we specify how exactly we are reducing the game, so for example, if we are reducing by iterated elimination of strictly dominated strategies, the word strictly is important here, then if there is a Nash equilibria in the reduced game, so in the reduced game, this is what we got, right? After reduction, this is what you got. The TR profile was the Nash equilibria. We verified that that is actually a Nash equilibria even of the original game. So that's the same thing that this result says. If the reduction is by this process, then whatever we get in the reduced game will also be an equilibria of the original game also. Meaning no equilibrias will get lost in the process of reducing the game by eliminating this way. Now here, if the game in G hat reduced to just one profile, some X star, for example, here we got this TR, so just one value, one profile, then that is actually going to be a unique equilibria of the original game also. For that game, it's the unique equilibria, obviously, but for the original game also, this becomes a unique equilibria. So these are some of the things that we saw in the first lecture, first week's lecture. Meaning we learned how to try and solve for equilibrias in games where there are dominant or dominated strategies. It's easier if it is strictly dominant strategies or strictly dominated strategies, then the elimination is valid. Otherwise, the order of elimination matters. So if there is a weakly dominated strategy, the order in which you remove it can make you lose or get equilibrias that you wouldn't have gotten in the game. But no new equilibrias will be created no matter what you do in the process. Okay, so these were some of the things we covered. Any doubts in this part? Like, if I'm to summarize, this is the main takeaway for week 1. Okay, yeah, this was easy. We've gone through this stuff a few times, so I'm sure you're comfortable with it now. So now week 2 was a bit different from all the other weeks because this was more formal. We talked about something called the Oman model, and this Ki of A was the knowledge operator. So what this knowledge operator basically said is, let me refresh your memory. This Y refers to the set of all the states, so all the states of the world. This Fi of W refers to, for the state of the world W, or for some state of the world W, what exact partition is it in. So all the ones that player I cannot distinguish between, so all of them grouped together that forms as fi of w. Now, if we can, if we only consider w's such that the partition of for player I of that W is less than the event or is a subset of the event, then we say that that event A is known to the known to the player I, or this represents the knowledge operator for player I for that event A. Meaning, if I were to go to the next step and say things like, say, ki of something else. Now, notice this itself is some state of the world, and these are by default a subset of y itself. It may be all of it, it may be just a part of it. Either ways, this also forms as an event. This can be thought of as an event, and hence we can always have ki of kj of a and actually other versions as well. So, what does this mean?
Player I knows that player J knows the event A.
So, if something shows up here, then that's true. If nothing shows up here, or if this is just empty, then that means player I does not know that player J knows the event A. Okay, so this is just trying to relate the language, the things that we are saying in words, to what we are writing in this formal form of the knowledge operator. Okay, so now there were a few properties that we saw for these knowledge operators. Some of them are fairly obvious. Some of them require a little bit of proof, but we've already done those things. So, the first property says that ki of A is always a subset of the event A. That is quite natural because we are saying the partition of some W for a player I is a subset of A. Hence, whatever we are going to get, whatever W's we are going to get here, have to be such that they all are in A and nothing extra is there. So, this has to be true. Okay, give me a second. Okay. Next one says that suppose there are two different events which are both some subset of the total state of the world, and there is a relation between those two events that A is a subset of B, then the knowledge operator will also preserve that same subset relationship. That if A was a subset, then the knowledge of A will also be a subset of knowledge of B. And this can be understood through a simple diagram also. So here, so here, take this orange region to be the event B, and this pink region to be event A. So now B is the superset of A, and the knowledge operator, to look at knowledge operator, we have to look at all those omegas or all those states of the world which cannot be distinguished, but they together are a subset of whichever event we are talking about. So first we have to consider, let's say the partitions are given by these black lines. So this would be the knowledge operator of event A. For event B, let's say in this particular example it turns out to be the same, but maybe if we had something like this, something like this. Then the knowledge operator for B would cover this region also, all of this region, and hence K2 of A is going to become a subset of K2 of B. So this relation also holds. Then if event A is a subset of the whole set, then player I knowing that he knows A actually is the same as him knowing that he knows A. So these two are pretty much the same thing. This is more like a definition thing and nothing more. Another possibility is if the event is the whole partition, if the event represents all of Y, or like as in all the states of the world, then for any particular player, no matter what the partitions are, all those partitions are actually equal to the event itself. Or in fact, any given partition is going to be a subset of the total uh, full partition, the full set of states. So this is by default true. This is the trivial scenario. That players know that there are some states of the world. They know what those states of the worlds are. Then this is a few more definitions. So this one says if we are to take an intersection of the knowledge operator of two different events, that is the same as taking the intersection of those events first and then looking at the knowledge operator of that for a player I. And similarly, this one is a slightly tricky one, but it's still the same as this result. So this is basically using 3, but here the meaning is to be very carefully looked at. There is a difference between this versus ki of A. Here player does not know, or rather player knows the complement of A. Here player knows the event A. So these two are very different objects, and in fact we can't compare these two also. Here the player knows the complement of A. Here the player does not know A. That doesn't necessarily mean that they have a relation between them. The only simple relationship that we can have when we're talking about the complements is using any of the previous properties, for example 3. Next thing that we saw was what is common knowledge. Common knowledge is in some state of the world, is some state of the world or some event which is known to the other people and that is known to all the players, or in slightly more funny language we would say player A knows that player B knows that player C knows that you go on through all the players, that there is an event A. That is the meaning of common knowledge, and this takes care of all sorts of weird combinations of knowing about an event. This is like saying that some information is available to everybody. Everybody saw that everybody knows this information, so kind of like an announcement made in public, and the public saw each other being present there and listening to that announcement. It's that kind of an object. So the kind of questions, some of the kind of questions that we saw in case of Omen model were following. So maybe we are given some players, some state of the world, and some partitions, and we are asked to calculate these knowledge operators. That's one kind of question we could get. Maybe we can try one of them, and I'll leave the rest for you to try on your own. It's very standard stuff. I think I might have I have actually copied this question from tutorials only, so it's not even a new question. So let's do this. Okay, we'll take the next part in a moment. That's anyways a next question. So here, event A is just state of the world 1. For player 1, state of the world 1 is distinguished from everything else, meaning k1 of A is actually equal to A for player 1. That's why I'm talking about sorry f1 of A. That means k1 of A, because they're equal, this just becomes A. Next would be to try and understand what is k2 of A. K2 of A means we look at any of these, for example. So let's say I'm talking about the state 1. Then what is the partition of this? The partition of this is actually 1 and 2. Player 2 cannot distinguish between states 1 and 2, and hence that's what it is. But this is actually a bigger set as compared to A. Meaning, from our definition of the knowledge operator, there is no omega such that this is true. Because that omega needs to be a part of A, and at the same time, that undistinguishable set cannot be a bigger than A. So this is 5. This is not true. We can't find anything. So player 2 doesn't know that event A has occurred, because event A is just state of the world 1, and he can't distinguish it from 1 and 2. So he'll not be able to know this. That also means, so from these two we can also say k2 of k1 of A, which is just k2 of A, I'm using this result, is just 5. And similarly you can try out other variations. This is the easier case. I've looked at only A. You could try out these kind of questions for the event B also. Any problems, any doubts, any confusions in this part? Okay, I guess not. Then other kind of questions that you could see could be, suppose we are given all of these details and we are asked, say the state of the world is w omega equal to 4, then can you find an event that will be common knowledge to all of them? So one way of doing this is to create a connected graph. Remember, in these situations, connected graph is basically, these are all the edges, so 1 to 8 are all the edges. If for any player in the game, if two edges are not if two states are not distinguishable, then you draw an edge between them. So based on this, 1 can't be distinguished from 2, this is for player 2. 2 can't be distinguished from 3, this is for player 1. 3 can't be distinguished from 4 by player 2, and so on. So this will actually end up, there is a slight error here. The partition does not include 8 at all. This might have been a typo. I'm just going to remove this. Yeah. So since overall the connected graph is actually all the states, what will be ck? Ck here is going to be the common knowledge. Here is going to be the event by itself, or the whole thing. There is no other event which can be common knowledge in this particular example.
Right.
Right? Okay, great. So yeah, that covers one kind of questions that you could see in this setting. Another could be in terms of belief. So suppose there these dots? Okay, give me a second. Okay, so let's say there is an example of this kind where we are being asked to talk about the belief of each of the agents about all the states of the world. So their belief is going to be restricted by what kind of partitions they have. So, okay, these dotted lines came up again. Anyways, so here these two are one information set, and these two are, let me not use the word information set, is another partition. This forms one partition and this forms another partition, and we are told the black ones are partitions for player 2 and these are for player 1. So maybe if you want to write it slightly more formally, this means player 1 cannot distinguish between 1 and 2, and 3 and 4. Player 2 cannot distinguish between 1 and 3, and 2 and 4. So now, uh, the probabilities that we're talking about, the belief probabilities, are based on, given that we are in a particular information set. So there is some true state of the world. So let's say the true state of the world is omega 1. If omega 1 is the true state of the world, player 1 would be in this information set. Player 1, he'll not be able to distinguish between omega 1 and omega 2. But player 2 will not be able to distinguish between omega 1 and omega 3. Which means whatever probabilities they talk about, whatever belief they form, will be based on this, whatever information they have. So these probabilities, the posterior beliefs, are probability of being in any particular state. That state can be anything, 1, 2, 3, 4, given the information that they have. So if this wk is not in their information set, whichever information set that we are talking about at a point of time, then the probability of that event is just going to be, probability of that state is just going to be 0. Meaning, for example, if this is the one that we're calculating, that means it can't be in omega 3 or omega 4. So these are already 0, and we just need to find out what are the probabilities for these two, and that is just Bayesian probability. That's all you have to solve for.
Makes sense.
Yeah. So if you do that, this turns out to be 1/8 by 1/8 plus 1/4 for omega 1, and for omega 2 the opposite, the remaining. And similarly you can solve for the other ones and fill this table. This is the belief of one player. Similarly, you can also create the belief table for other player, but then the information that you have to be careful about is their information set. So the information set of the player 2. And these
Sorry.
hmm,
So it this could like why is this by 8 and 2?
what?
Why is this 1 by 8 and not 1 by 4? Like probability of W1.
Yeah, so probability of W1 is basically getting W1 divided by the probability of those two. And probability of W1 is 1 by 8 here.
Oh, right. Okay. Then I understand.
Okay, okay. Okay, so that's about this. So similarly, you can do it for player 2 also. So that gives us player 2's posterior beliefs. Any questions till this point? Okay.
I think I'm good.
Okay, no problem. So then let's go to week 3. Now, week 3 was basically talking about zero sum games, security levels, and what do we get from security levels, the min, max, max, min values, and so on. So, in a nutshell, what it was doing was so here we are assuming we are taking the first player to be minimizing, meaning the row player is minimizing, the column player is maximizing. That means row player would want to try to find a level, the worst possible payoff he could get. He knows that he will do his best, but he has no control on what the other person will do. So what he's going to look at is the max expected utility that he could get if the other player is the one maximizing. So basically that means looking fixing a row and looking through these values and taking the maxima from there. So here it's 5, here it's 3, and for the last one again it's 5. And for him the next part is from the worst possible payoffs that he could have gotten, he's going to try and minimize the worst case scenario. So he ends up getting 3. That means for him the security level is okay, so I star is 2 here. And similarly, exactly same logic but turned opposite is for player 2. Player 2 is interested in maximizing his utility, meaning he wants to have a security level that tells him that my best expected utility is not going to be lower than this particular value. That much freedom, that much choice I will get every time. That means what he'll do is he'll fix a column and look at the minimum value from that particular column, so going through each row. That means for the first one he'll get 3, then he'll get 2, and last he'll get 1. And since he himself is maximizing, so he knows that he can at least between to have a choice between these 3, he'll at least choose 3. So for him the level would be, the security value would be rather 3, and the security level turns out to be security level is which one? This one.
1.
1. Yeah. So in this scenario what happened is both of these min max and max min ended up being equal, and what we got is actually a Nash equilibria, which is I comma j, that is 2 comma 1. This is a Nash equilibria profile. We can verify that by checking for it. Another way to think about Nash equilibria is to talk about saddle points. They say a saddle point is such that, suppose there is a profile I star j star, then if you compare through the row, then whatever you have is the minima. So for example here, if you consider this is our, so my claim is this is our saddle point, then what you would do is you will compare, oh right, you're fixing a column and you're comparing the values in each of the rows, and you say that okay, here is where you get the minimum. So this part of the inequality. Then this part of the inequality says that if you were to do the opposite but fix a particular row, meaning you fixed I star here, then whatever value you have is actually going to be the maximum possible values from all of them, or it might be equal to other highest values. And that's what this means. Meaning, so because this is satisfied on both the sides, that means this I comma j that we have is actually a saddle point. And if you recall, we saw the proof of all of these things also. If these two levels, the min max and max min levels, are actually equal to each other, then a saddle point exists, and that saddle point is actually same as the security levels, and that is the Nash equilibrium of that particular game. But in general, the relationship between these two levels is that the V bar is greater than V under bar. So there is like a gap here. Or you can think of it this way. Here, what is happening? We are maximizing first and then minimizing. So this value is going to be by default bigger than the scenario where we are minimizing first and then taking the max from there. So that's the security level, that's the kind of levels that we're getting. Now, what if here what we got was we just got one security level for each player? That's not always necessary the case, right? We could get more than one security level. So for example, the only thing that I've done is from the above example I've changed one number. Because of that, if I fill all of these things again, we get 5 here, 3 here, 5 here. So nothing changed. I star is still 2. So that's player 1 should still be playing strategy 2. But what about player the column player? So column player would be looking at these. The minima here is still 3. The minima here is 3 now. Minima here is 1. So this is 3, 3 and 1. Now that means J star is both of these because they're equal. That means we are getting J star to be 1, 2. So in the scenario where we get more than one security levels, we know, and if V bar of A is 3, V under bar of A is again 3 in both of these situations, if they are matching, means if they're really saddle points, so we have to verify that they are. If they are, this one is a saddle point, we already know that. We just need to verify if this is also a saddle point. So comparing with the fixed row, this is the highest possible value because actually it's equal to another value, and from here this is the lowest possible value. So this is also a saddle point. So what happened here is I comma j, that is 2 comma 1 and 2 comma 2, both of these are saddle points. And if both of these are saddle points, that also means that both of these are Nash equilibriums. And notice this is one of the theorems that we had seen, that if there are multiple Nash equilibriums in a zero sum game, the value of the game would still be the same. So the value of the game here is 3. So this is the scenario with multiple security levels. Okay, then next thing is mixed strategies. Here what is required is that V bar of A is equal to V under bar of A. This is required for us to be able to talk about Nash equilibriums, but this can't be true in general. So one way to sort of handle this gap, the gap between V bar of A and V under bar of A, is to bring in some randomization in the problem. Randomization in the problem means we put probabilities for each of those pure strategies available to us. So for example, here it means we assign some probability to all these actions, or we assign probabilities to all these actions, and then look at expected utilities and compare expected utilities, and then talk about equilibriums. So if that is done, that is called as mixed strategies. So let's say for player 1, I'm saying the mixed strategies is denoted, the set of mixed strategies is denoted by this y, and for player 2 it's denoted by this z. Then the expected payoff is y transpose A times z. A is still the payoff matrix, and z is the utility, z is the probability distributions for player 2's set of actions. So here again we can have security levels. Those security levels would be by the same logic, so we are still assuming that player 1 is minimizing. I think that's what we had. Yeah, player 1 is minimizing and player 2 is hence maximizing. So the security levels can be of the following form. So instead of minimizing or maximizing and meaning choosing one row or one column at a time, this is going to be choosing the actual value of these probabilities from these set of valid probabilities. So any probabilities that is valid for that particular problem. That means we take, so if we are talking about the security level for player 1, we would be basically looking at y star such that we take the maxima of this with respect to the utility of the probability of the other guy or the strategy of the other guy, so player 2, and then from all of them, whichever y star gives the minimum value, that's our security level, or that gives us our VM of A. And similarly, we can define the security level and this security strategy for player 2 in the opposite way, as first taking the minimum with respect to y and maximizing with respect to z of the expected utility. So what this does is, now in the earlier version we had these two as the security levels or the security strategies corresponding to those security levels. Now the security levels are both reduced and the gap reduces depending on which particular mixed strategy we're getting, meaning it can happen that there can be a situation where these two match. And in fact that is the core theorem, that is Nash's main theorem, that says for any game, it this particular theorem is true for zero sum games and non zero sum games. We may not have seen the proof for non zero sum games, but it is still true. It says that for any game, there always exists a mixed strategy Nash. Obviously we're talking about any static finite game. Finite meaning finite number of strategies. It's true for even infinite number of strategies, but we're not getting into that part.
Right.
Yeah. You had a doubt in week 3, you were saying?
Yeah, that was that question. So basically, I think we solve this question of a zero sum game on unit square, and the payoff was defined by a function of xy. So, is it possible that you can just open up the notes that for week 3 and I can just show you like where I had the doubt and what is it?
Yeah, sure. This was week
It's also
3.
pretty
You
different.
should have the notes. Did we do it in
On
week?
page 10 or something. Which we do.
Was it week 3's notes or week 4's note?
That was week
If you see it, just stop me. I am not able to see where this unit sum question is. Unit square
That was
question.
week 3 only. I don't
It's week 3? Oh, okay.
know. On
Page
page 10, so
10. Okay, yeah. Yeah. What was your question here?
yeah, so basically, okay, so we have to find this. So first of all, like this x and y, this here it means that can take any value between 0 and 1, right? The
Yeah.
continuous thing. Okay, and then like okay, so then when we minimize this, so we add a condition, like if we go down a little, then yeah, so notice that like when we are minimizing this, then we add this condition x is greater than equal to 1 by 4. In
Ah.
case of, so
Hmm.
that part I did not get to get.
Hmm.
Let me go through
Okay.
this as well.
So okay, what I think is happening here is we are looking for security levels. We are told that XY are the strategies. So you can think of these as a kind of mixed strategies only, because these are values between 0 and 1. So they're pretty much like probabilities only. So you can think of it that way.
Right.
And the expected utility, you don't have to calculate it. You're given a form of it in terms of X and Y, which is this
Yeah,
object.
that makes sense.
So all you're supposed to do is solve for these things. So find the security levels for both the players. Which one are we doing first? Okay, I think we're doing this one first.
Yeah.
So here, from here to here, all that is being done is looking at what is the coefficient of y.
Right.
Right, now look at this particular coefficient. If this coefficient is positive, meaning x is greater than 1/4,
Yeah.
in that case, what would be better for you? What kind of value would you choose for y? Wouldn't you prefer y is 0?
Okay, so if x is greater than equal to 1 by 4, then this is a higher value and we want to minimize it. So in that case, we prefer a guys. Okay.
Yep,
Okay.
which means this is gone and all you're left with is this term, exactly this.
Okay. Okay.
Okay.
Yeah, because actually if you say what kind of y is equal to 0, then why does condition matter anyway? To kind of simple, right? Like if y is equal to 0, then anyways first this one, that part itself gets cancelled. But now what you're saying, that makes sense, that we are first checking what y should be, and accordingly we are designing the value, what x should be, and accordingly we are designing the value for
Yeah,
y.
because the value of x decides what this coefficient will be. If this coefficient is negative, then it's best to keep the maximum negative here. And in
Okay.
that sense, it would be helpful to have the maximum value of y, which is 1, and then simplify it. Okay, so that's pretty much what is done here, and that gives you these things.
Okay,
And
and then
so
like once we get minus 2x plus 3 and 12 plus 3, and then when we want to test is that we want to maximize this. So,
hmm. So from here we want to maximize these two. Now try and remember how we did it for mixed strategies. We had two lines on the graph, and all that actually mattered was in maximizing or minimizing was to find where they were intersecting. We were, I think, minimizing in that. That's why we were looking at intersection. So
yes,
similar
yes.
thing you're doing here also.
Okay, okay, okay. So we are like what? Like equalizing that thing.
So yeah, so if you take x equal to 1/4, which means you should be looking at both of them together, then what you get is this object.
Okay.
That's the maximum you could get.
Mm.
Otherwise, this is decreasing with x, but your x is increasing. So this object is decreasing more and more. And this object is increasing, but your x is on the lesser side. So from
Okay.
0 to x equal to 1/4, it's increasing, but at 1/4 is where there is a peak, and then it's like this. Like these two, if you were to draw, not exactly, but roughly, it would be this way. This is 2x plus 3, this is minus 2x plus 3, and this is happening at x equal to 1/4. You could try drawing it out if you want. You'll
Okay.
get the exact slopes and all of those things more precisely.
Got. Okay. Sure.
Yeah. So your doubt is cleared? Nothing further here?
Yeah.
Okay.
No.
Okay, perfect. I'll go back. Where were we? Yeah. So this is the security levels in mixed strategy. So we can do the same thing that we have done in pure strategies, and we can do that in mixed strategies also. The theorems and results that we had for pure strategies, there are similar theorems and results even for mixed strategies. The main key point that you need to remember is that is the main theorem of Nash, which says that in any static finite game, there will always exist a mixed strategy Nash equilibrium. So that means when we use the word value of a game, if pure strategy value does not exist, meaning that there is a gap between these two, then what you're looking for is VM of A, which actually equals this Vm of A. So that particular mixing of the strategies, the pure strategy, such that you get these two to be equal. When that happens, that becomes the value of the game. So you may have seen the word value of the game used without saying whether it's pure strategy or mixed strategy. That's because for pure strategies, you just will see that these two become equal and that becomes the value of the game. In mixed strategies, you need to find or find the probability such that these two become equal, and when they become equal, that particular value is called as the value of the game. So that should tell you that this is, you first should look at pure strategies and then look at mixed strategies. Okay, so this is one example where perfect. So this is one example where in mixed strategies you were calculating how to find these, how to solve for these mixed strategies, as in how to get the value of the probability y and the probability z. That means what you're going to do is you're doing the min max, and while doing the max, or whatever is the inner, the first operation that you're supposed to do, you do that operation a little bit more carefully, and instead of, so if it is over z, you just take z to be either 0 or 1, or if there are more values, so take it to be accordingly, but the value has to be for any particular strategy 0 or 1. So meaning you're fixing one of the, so in this case it means you're fixing one of the columns, and then you're calculating the expected utility for that fixed column, and then you're repeating that for all the columns. What that gives you is, ultimately you're supposed to make sure they are equal, and that is saying the other player will not benefit from, will not have a good best response to this. They will be okay with either of them. That's the equality that you're doing. So creating a situation of a saddle point, that's what this means. So now it can also happen that there are more than two strategies available to you that are to be mixed. So that in diagrammatic form could mean something like this. There is one, uh, so this refers to this object. Okay, so I'm drawing the expected utility here with respect to y and z. Maybe there is one more which is like this, and there is one here. Now it depends what you're trying to do. If what you're trying to look for is this object, you're maximizing these, then you have these three intersection points, and you need to just compare which of them gives you the maximum value. So here that maximum value is coming from here. So see if
Can you
that is,
please repeat about how do we get the maximum and minimum value from the graphs?
okay. Are you okay if I go to an example from this week's lecture? Maybe this itself. I don't
Yes,
want to
ma'am.
do it in detail. Uh, this is still week 3, right?
Yes.
Okay, perfect. Um, okay, week 3 doesn't have this, I think. Week 4 has it then. Okay. Let me take the example that I had copied. Yeah. So you're with me up till here, right? Um,
Yes.
Mananya, right? So you can get these expected utility values, all the expected utility values for all the different strategies for the other player. So for all the columns, all those values you can get. So for example, these are the two uh, situations you get. Now what you need to do is you need to take the max of these two. Taking the max of these two means you want to choose, so if you were to plot them, you could plot them. So here what I've done in the plot is you are plotting the utility on this side and the y value on this side. The y value would range from 0 to 1. So in that region, what do these two look like? So let's see what is happening here. Huh. As y is increasing, this object is increasing. That means this one must be 2y minus 1, and the other one must be 1 minus 2y. So the maxima of these two in the sense of the graph means that till the time you are below whatever this intersection point is, that turns out to be half, but whatever that intersection point is, it's better to choose this strategy, meaning it's saying play L up till this value of y. When the value of y is beyond that, this is what you should be doing.
Okay, ma'am.
If you recall, the idea here in looking for mixed strategies is to sort of confuse the other player and choose a y. So, for example, here, choose a y such that the player has no real choice. No matter which pure strategy he chooses, he doesn't benefit from it. For him, they're both best responses. And that's exactly what happens if you take y to be half, because then at this point there's an intersection and both of these are the same. There's no maximizing to be done, they're the same exact values. And once you've done that, you get the utility, you get the value of the mixed strategy, one of them. Then you repeat it for the opposite side, meaning this time instead of fixing the columns, you fix a row and look at this object with corresponding z's. Fix a y value, so you're taking y equal to either 0 or 1. That's pretty much what is happening. And then same thing, in the process of trying to compare them, you ultimately see when are these two equal, because when these two are equal is when you're going to get this result, max min scenario, and that will happen for some value of z star. For this example, both of these end up being half, and that you can see because the values are symmetric, they're ones and minus ones.
Yes, ma'am. Thank you.
Yeah. Okay, perfect. So now, okay, before I go to week 5, let me go through the question one of you had asked. Okay, this is week 5. I'll come back to this. So from week 4, there was this one question that I think Mananya, you only had asked to clarify. This is question 1 and 2. 1 was simple, 2 is the more important one. So for question 2, what they're saying is, suppose there's a graph. All the vertex of the graph are actually the pure strategies, the set of pure strategies for both the players. So let's say x represents player 1, y represents player 2. Now whether there is a edge between them, there is a condition to be satisfied. If there is a edge between x and y, then there is no edge between y and x, meaning if so this is actually saying that this is a directed graph. If suppose this is x1 and this is y1, and if there is a edge between them, the opposite edge does not exist, meaning it's not undirected. And they're actually using this condition in many different versions. So then they define the full utility matrix. The utility matrix says that if x and y are equal, as in it's the same one, they are allowing a loop, they're allowing a edge on the graph itself. Self looping is allowed, that's what this means. For that, the utility is 0. But for the other one, for the situation where x and y are not equal and there is an edge, then the utility is 1. On the other hand, if xy doesn't have an edge between them, then the utility is -1. So you can see what this means. If suppose for some xy, so for the whole matrix, the diagonal entries are by default 0, that is sorted and done. Suppose here it was 1. So this refers to some x and some y. This is 1. If this is 1, then this one has to be -1.
Yeah.
Because this portion does not have an edge. And similarly, if you go through the whole thing, you'll see that this is skew symmetric. Now,
Yeah.
what they're asking in the question is something about this Q star, the optimal utility. some condition that they've written, and they're just asking which of those inequality or which of those conditions need to be true. So for that, yeah, uh, the value of this game, because this is just going to have zeros, ones, or 1 or minus 1, the value of this game is just going to be 0. And you can see that by taking uniform probability for both y and z, for both the two sides. Now what we require is this object. Where is it? Hmm. Okay, so if the value of the game is 0, that means for this optimal q star, uh, the q star is optimal for the column player. So for the q star of y, this object, the expected utility, has to be greater, less than or equal to 0, because this player is minimizing. The column player was minimizing. Hmm.
So here, this u of x comma y, like, so we are picking one row and we're going across it, like we're traversing on it. Is that like this u x y? Is it that, or is that right?
Sorry, come again.
So basically, this summation of u x y into q star of y, this is a summation over one row, is it?
This summation.
Yeah, this.
Uh, no, not exactly. So this q star of y. Okay,
So the summation, I mean, we're taking across all edges, or like across all edges or across all
So what
vertices.
would actually be happening here is q star of y means that we are giving some probabilities to y. So each of these has some probability assigned to it.
Okay.
So yeah, okay, yeah. It needs to be true for all x. So you take one row at a time and then do this. Hmm, correct. So you're taking the expected utility here. You have these q star y probability values, and then whatever is the corresponding utility there, one of those values, 0, 1, or minus 1, and then you're just taking sum of all of them. Okay, so now there are these things that were defined in the explanation of the answer. So one of the scenario is the case where the utility is 1. The utility is 1 when xy have a edge between them. The case when xy have a edge between them is sum of all of these things. Okay, so the opposite scenario is if y and x don't have an edge between them, or rather, if x and y have an edge between them, that means y and x will not have an edge between them. So for those y's, you can say that this refers to the probability, and if you just multiply it by minus 1, you'll get the utility, the expected utility, at least a part of this expected utility.
So Q star y is zero, you said, right?
Hmm?
Q star y is zero, is what you said, right?
No, q star y is not 0. I'm saying this expected utility is
Mm.
less than equal to 0, because the value of the game is 0. That means this is going to be either less than that or equal to 0, because the player is minimizing, the column player is minimizing.
Okay.
So he would want, see, value of the game was the security level, so he would want whatever he does is at least better than that if he can. If he's not able to, then that's it, that's over anyways. That's where he's going to try and reach. So Basically, what is happening here is we are breaking this down into three parts. The three parts are the following: P out, the scenario where utility is 1, those particular q stars or those particular columns. The columns where q star is actually, q star is fine, but the utility ends up being -1. And those particular scenarios where you're supposed to look at kind of a self loop, because what is being asked to you in the question, or if you look at the options given, the object is this q star of y, and y can be any of these edges, but they're not saying that y can't be equal to x, so that is actually included, and that is referring to some extra quantity. And it's these three probabilities, the sum of these three probabilities, that must be 0.
Okay.
Sorry, sum of these probabilities must be 1. That means we can say that hmm, yeah, that's the mistake that I was thinking happened here. So P out is this object. There is an edge, but x is not equal to y. That means this object that we're looking at is the sum of those where there is an edge, but x and y are different, plus the probability of being in the state x, whatever that state x is, meaning whichever row we are in, that diagonal entry from the whole thing, that particular, what is the probability of being there, that's q star of x. And we can say, again, we can rewrite this by using the relation between P out and P in. Probability of P in is greater than probability of P out. That means if we replace P out by P in, this becomes P in and we can say that this object is equal to this quantity and q star, and that ultimately means that we have uh, some q star x value, some probability of being in that state x, but whatever that is going to be greater than or equal to 0, meaning this object is greater than or equal to half. So the main thing over here was to just be able to, you don't have to worry about this p in and p out, you just have to be able to break down this into the different parts it has, and then be able to compare the two parts, and that comparison allows you to have a kind of a inequality relationship.
So both the parts that you took were both the cases where x is not equal to y, but it's an edge.
Sorry.
In P out and Pn, like
Mm-hmm.
both the summations that you took. So in both the cases, x is not equal to y, but x comma y is an edge.
So here I've taken x comma y is an edge, here I've taken y comma x is an edge, meaning x comma y
Okay,
is not an edge, meaning it'll have the utility -1.
right. Okay.
So I'm sort of breaking this down into two parts, that's all.
Mm-hmm. Yeah, okay.
Okay. uh does this clarify things for you, Mananya? You had doubt in this. Okay, perfect. Now let's continue with week 5. Okay, so week 4 basically talked about, it ended by talking about mixed strategies in zero sum games. The same idea of mixed strategies can be applied to non-zero sum games also without even having to worry about security levels, and that is done by, it's the exact same idea, and it looks like this. So for example, you talk about this case, you fix, for example, no, this one is written in terms of fixing this. So you fix a row, so you fixed this object, so you're doing it for player 1, for example. So you're fixing one row, and then what you're doing is you're saying these two expected utilities should match. The expected utility from here and the expected utility from here should match, even if the other player plays whatever strategy he wants to play. And that sort of pushes this queue to take some value, which is equating these two objects. This is exactly what we had when we were doing the process using graphs also, which is to ultimately equate these two to be the same, or whatever we would have gotten here to equate those two expected utilities to be equal to each other. And when you do that for all the players involved, you would get what should be the randomizations, the amount of randomizations required, and you'd get the mixed strategy distributions from that. So the same thing can be extended to non-zero sum games also. Now when it is expanded to non-zero sum games, what we are getting is these utilities come from, these utilities or these expected utilities are coming based on some kind of an extreme idea that you're saying players would always choose the most optimal thing, but sometimes it is okay to choose something that is suboptimal and have a kind of a response function. And this is captured in what is called as these quantile response models. So these quantile response models, what do? They have these mixed strategies of any player, they have these set of mixed strategies, and they define these objects called VIJs, some quantum response functions. And using these, this is just the expected utility with respect to the strategy of all the other players, where where the ith player is playing some jth strategy. So understand, this is all still talking about finite strategy space. Then this Qij is the ith player playing jth strategy. This is a kind of a response model that we are choosing. This response model is something that can be different. This is a simple response model. It's like saying there are two intensities of light. I want to give some sort of probabilities to those, and hence all I'm doing is I'm taking a simple Bayesian type probabilities to those. So I'm converting those intensity values into probabilities using kind of Bayesian rules. That is one kind of response function. There can be other kinds of response functions, and in fact there was a question on this, so I'll quickly walk you through that. 1 second. Was the question from assignment 5? So for example, something like this. So you're given a game and you're asked to, given some quantile response function, you're just supposed to find these Vij type of utilities. That is basically solving for these expected utilities of the other players. If all the other ones are playing mixed strategies, but this one player decides to play sorry, all the other players are playing these quantal response type strategies, and this one player is playing a simple pure strategy. Then what are these utility values that you'd get, or what is vij's, and using those you can calculate for these sigma ij's. So for example, in this question, so they're defining that, let's say sigma 1 1 is p and sigma 2 1 is q, meaning the other is 1 minus p and 1 minus q. This tells us how we can go about talking about what is v11. V11 is the expected utility of player 1 when player 1 plays strategy 1. So player 1 is playing this strategy, so he's here. So for him the utility is 2, and player 2 is playing whatever it wants, meaning it's actually playing this one with probability p and this one with probability 1 minus p. So this ultimately gives us v11 equal to 2 times q. That's exactly what is written here. And similarly v12, meaning player 1, oh that was from here. Player 1 is playing this second row, and player 2 is playing q, whatever that is. Here he gets nothing because the utility is 0. In the expected utility, this is all he gets, so this is 1 times 1 minus q, and that's exactly what he got here. And similarly you can calculate for the other ones. By simplifying, you will see that p and q have a relation between each other, and if you solve for both of them simultaneously, that will give you that p has to be either 0 or 1. And because 2 2 is a higher utility, that's the one that will get chosen, and hence p and q end up being 1 comma 1, or rather it's the first answer that's true. So this is one kind of quantal response function. Another kind of quantal response function could be like this. So there is some lambda that comes up, and that defines what is happening. So you're supposed to repeat this exact same thing of calculating these v1 v11 v12 v21 and all of that. Calculate all of them and then plug in the simplification for these and solve for the optimal q11 and q21. This is a bit of algebraic work, so I'm not going to do this. Try to go through these steps and see if you can understand, but the idea is the same as this example. The algebraic steps in this particular example take quite a while to get. Okay, perfect. Yeah, so I'll move on. One second, I'll share the other screen again. Okay, this was week 5. Then after that we started talking about extensive form games or dynamic games. So what we had seen so far were static games where the players didn't know what were the actions taken by the other players, or they were simultaneous move games that the players were playing at the same time, so they didn't know what the other players played, and hence their own actions were based on their information. They were not looking at the action of the other to decide their next step. But when players can know when suppose player 2 knows what player 1 has played, then the set of strategies that he has available expands, and he can choose what to do depending on where he is in the game. So in these type of scenarios, we can solve for it, as in look for equilibrias, in two ways. One is to write the normal form, another is to do it recursively. We have actually solved a lot of these examples, so I'll not go through all of them, but uh, one of the doubt question is actually of this kind only, so I'll go to that next. Give me 1 second. um, that was week 8. Okay, this was one of the questions. So this is question 1 from week 8. Okay, so if you are asked to solve for it in normal form, what that means is you're supposed to write the full matrix, and that means you're supposed to look at all the strategies. So for here, player 1 is the brother, player 2 is the sister, player 1 has strategies. Okay, I'm just going to give them numbers 1, 2, and 3. Player 2 can play ANR, but she can play ANR at 3 different points, meaning it's supposed to be a Cartesian product of ANR, and actually 3 Cartesian products. That means the set of strategies here becomes all of these things. So AAA, AAR, ARA, and last R. Okay, so what you require to do in normal form means you need to make the matrix. So consider all of these. So I'll not fill the whole thing, but I'll tell you how to fill some of it. So for example, let's take AAA and AAR, and I'll leave the rest of it for you to fill yourself. So this is 1, this is 2, this is 3. Okay, so now what is happening, what this AAR means, this is at node 1, node 2, node 3. So node 1, node 2, node 3. So the first one is simple, it's the same step in all 3 of them. So anyways, it's just this one, or this one. That means here we get 2, 0, here we get 1, 1, and last we get 0, 2. Okay, if you were to go to some other strategy, for example AAR, this is saying here player 1 plays A, player 1 plays 1 and player 2 plays A. Okay, here again same thing, so again okay. Here instead of playing A, R is played. So what that means is this leads to 2, 0, 1, 1, and the last one is 0, 0. And with this kind of logic, you have to fill the whole thing. That's going to be a fairly big matrix, and then search for Nash equilibrias from that. So searching for Nash equilibrias from that means you have to do the same thing, pick a column and choose which one maximizes the most. So it's this one here, and so on. And then now since I've not created even one column completely, so I can't do that, but you have to go through the columns and compare which one has a higher payoff, then find
The
what are the
payoffs are,
equilibrias. Yeah.
when the payoffs are equal, do you consider both?
Yes, because they're equal. The Nash equilibrium never has just a strict inequality. It's always equal to, less than or equal to. So equal is to be considered.
Okay.
Okay. So if you go through that process, you will see that there are, I think, 9 Nash equilibria, meaning in normal form. You'll not be able to find all the ones from recursive method, but if you make the matrix, you will get all the 9 or 6. I don't know what the number is. The number is written in the answer. The second thing that,
That's
sorry,
yeah, it's nine.
it's 9, right? Yeah, okay. So verify that it is actually 9, but I hope it's clear how to fill this matrix. Vivek, is it okay? You'll be able to do the rest of it? Okay, perfect. So I'll continue. So the next thing here for you to do would be to solve for this in the other method, which is the subgame perfect method or backward induction. So backward induction basically says at each node you let players decide what to do. So here we let the player decide. There are no information sets, so we are sorted. So player 2, player sister, would say, okay, I'll choose between these two. So for her there are two choices, but it's actually equal choices. So she's fine with choosing either of them here. Here again, are they both maximizing in the question? Can you just verify?
Yes, ma'am.
They are maximizing? Okay. So here she has two choices. Here between 1 and 0, she would prefer 1. So this is one choice. Here again, she has one choice. That means we'll have to do this process properly. So let's say in the first scenario, sister chooses this one. So she chooses 2 comma 1 for the first. This is the second option. This is the third option. Here these were the only ones. Now player 1 needs to choose between these three, and hence player 1 will end up choosing this. That's one subgame perfect equilibria. Okay, so right now what I'm pointing at is the payoff. If you were to write the strategies, you'll have to write it a little bit more carefully. So what is actually chosen is player 1 has chosen 1 and player 2 has chosen, okay, actually player 2 has chosen AAA, and player 2 actually had a different choice. So if player 2 here had made the other choice, then this becomes 0 comma 0, 1 comma 1 and 0 comma 2. Then player 2 would prefer this one. That means this is, for player 2 the strategy is 2. For player 1 the choice became RAA. So what this is doing is we get two subgame perfect Nash equilibrias here. Okay, so the point is whatever you got here, you would get these two as best solutions even in normal form. So from these 9 we already found 2 of them. There are other 7 that you'll have to search for more carefully.
Okay.
Okay, yeah. So this was week 8 where we talked about extensive form games, and these were simple extensive form games, meaning there were no information sets or anything, just straightforward things. After that, in the next week, we started talking about information sets. Information set basically means that a player, for example player 2 here, will not be able to distinguish between which node he's at, whether he's at this node or this node, meaning he could not see what action was played by player 1 over here. He can see that it is not R1 if he's in this section, but he can't tell whether L1 was played or M1 was played. For him, somehow those two became similar, and these types of games are called games with imperfect information. On the other hand, games with perfect information are, for example, what we saw earlier. In other words, you could say games where every information set is a singleton. I'll just write the keyword. That's when a game is said to be of perfect information. If that is not the case, if there is even one information set that's not a singleton, then that's a imperfect information game. Here again, the solution concepts are the same. We have two possible solution concepts. One of them is to search for the normal form. The other is to solve for it by backward induction. But here, normal form needs to be looked at a little carefully. Now, let's take this example again. So, player 2 is the more important player or the more interesting player. Player 2 cannot distinguish between these two nodes, meaning whatever action he takes here has to be the same action. So here he does not have two choices, he has only one set of choice, and that is whatever L2 R2. But at this node he does have extra choice, so that's another thing. So that's what we can take the Cartesian product with. Or to even make this point clear, let this be L3 R3. Okay, so we have to do the exact same thing. Normal form means this is our strategy set for player 2. Player 1 has only 3 options, so we make the table and search for it from there. That's process number 1. Process number 2 is backward induction. Now for backward induction, what we were doing, we were taking a node and just choosing between the two options. Here I did not specify, right? So this is written as a zero sum game. And on top of that, let's say what we are given is the utility of player 1, and let's say player 1 is maximizing, and hence player 2 would be minimizing. So this node is okay. Here player 2 can actually make a choice whether to do this or do this. That is sorted. But here there is a confusion. Player 2 does not know which node he is at, so he has these options. Now this portion of the game can be captured as a static game, meaning I can write that portion. So I can write this portion in the following form, what we call as, what do we call it?
Normal form.
Normal form, or rather simultaneous move game, because this is only that portion, the sub portion, L1 M1 L2 R2, and then it's just filling this. So this is 3, this is, and then we just are required to find equilibrium if there is one. If there is an equilibrium, that's the strategy. For example, this is randomly I'm saying, so for example it's this one, that's the one that gets chosen, L1 L2. Then the decision would be between L1 L2 and, for example, R1, and between these two player 2 is minimizing. Okay, player 2 would end up choosing 0, so the decision would be between this and this, for example. And that's the process of doing it by backward induction. So what we did is, if there is some information set which is not a singleton, then you need to look at the subgame meaning go up till the point where there is a singleton node, only then you stop, and then whatever tree you have at the bottom of it, so for example this one needs to be taken as one full thing. You have to choose what that needs to reduce to, what utility it reduces to, or what actions or strategy lead there. So you have to solve that as a simple normal form. There is nothing else that can be done. And same idea as before, whatever we would get as equilibria in backward induction, that would already exist in normal form, and here there might be more. One important thing to note here is, if this information set did not exist, and if we were to compare those two games, with the information set, with this X information set, and without it, then the equilibrias are basically being compared in a proper game and a informationally inferior game. So if there are some equilibrias in the informationally inferior games, those will always exist in the original game. Okay, this is one of the results actually that comes up in, I am guessing, week 7 only.
Yeah, makes sense.
Yeah. Okay. Then we talked about a few definitions, which were nested, ladder nested, multi-act games, feedback form games, and all of that. So let's just quickly revise those points. So nested. Sorry. Yeah.
Sorry to disturb you again, but like I found out in week 7, question 5 assignment. Okay.
You had a doubt in week 7, question 5. 1 second.
Hmm.
Um, yeah.
So, I maybe had a doubt on the fourth part that the total number of strategies available to player one is significantly greater than the total number of possible games. So, if you can, this is a tic-tac-toe one. So,
Yeah.
uh, like if you can just tell me this thing.
So what is happening here is, this is one thing that you need to understand. This is not a game, a single act game. Tic tac toe is a multi act game, so players are playing again and again. But this is still
Right.
like a feedback form, so it's okay. So now, if players are playing more than once, the strategy counting is supposed to be done very carefully. At every node, you're supposed to take the strategies and take the Cartesian product of all of them, and that's required. And hence, when you come to the bottom of the tree, you get a whole bunch of leaves. Now, I'm just explaining the first part of the question, and then I'll come to yours also. So this is saying, this is first asking what is the number of leaf nodes. Now, any player would get to play as many times until the board is filled. So there are total 9 boxes in the board, and either all of them get filled and the game is over, or somebody wins.
Right.
We're not saying that at a tie they stop. Realizing that the game is not going to end, they don't stop with that, they still continue filling it. That means the number of leaf nodes are not going to be the maximum ones, which is 9
9
factorial.
factorial.
It's going to be less than that. Now, what is happening to the strategies of each of those players? The strategies of each player are related to how many turn off my video.
Okay, so it will be like
Yeah, you're looking at
let's
all
say
of those paths. Those number of paths are to be considering all of those possibilities. Suppose at one node he had 9 options available, which was, say, the first one. He's the first player. When he has 9 options available, he's choosing from them, and then the second time he gets to play, if he gets to play, then he'll have 2 are gone, 7 options available, and then he gets to play again, and so on. So this is 9.
Actually, that will be in power. Now I get it. So,
Yeah.
like in 7, it will be like 7 to the power something, not just
Because
the
it's
factorial.
exponentially exploding, so he has that many options. Those options are exploding. The final ones obviously are at the bottom.
Right. This is like the previous question, question 1 of assignment 8, where we had 2 into 2 into 2. So that's why it will be a good number. Now I
Yeah.
get it. Yeah.
Okay, 1 second. Okay, so we are at week 8 now. Okay, ठीक है. As long as we manage to cover till week 10, I am okay with it. Okay, week 8. So in week 8 we just talked about some simple definitions. So, for example, nested. Nested basically says each player has access to the information that its predecessor have. Player who's playing last can know more than players who played before him, but he has to know at least as much as players who played before him. So for example, take this one. Is it nested or not? Player 1 doesn't know anything. Player 2 knows which action was done by player 1. Okay. Does player 3 know that in each of his nodes what was the action of player 1?
Yes.
He knows that in each of these information sets. So he knows as much as player 2 knows and as much as player 1 knows. So just by that, it's nested. Now, is it ladder nested? Ladder nested is basically comparing the information of these two. The only difference in the information of P2 and P3 should be action of P2. Is that the case? So at this node, here he knows the action, here he doesn't even know that. So there's no difference in what they know, so this is sorted. But here he knows that. Here again he can't tell the action of P2. That means this is ladder nested also. Okay?
Yeah.
Okay. Then the other kinds of things that you must have seen in week 8 were questions of this sort, where you're given some extensive form and you're asked, okay, tell us the number of subgames, tell us the number of subgame perfect equilibrias. And these subgame perfect equilibrias are the exact same idea as what we had here. If, like here, if there were more than one choices at any of these sub games, then we get more than one sub-game perfect equilibrias, and that's the exact same thing that would happen in games of this kind also. Even if we have to, so this portion or this portion has to be solved as a simultaneous move game, but still, if the simultaneous move game has more than one Nash equilibrias, then this becomes a game of that kind. So there can be more than one sub-game perfect Nash equilibrias. Okay, the next thing that we saw in this lecture was what is a multi-act game and what is a feedback form game. Multi-act game just means that players sort of have a stage in which all players get to play max once, and then there's next stage where again players get to play max once, and this sort of continues. That's multi-act. Everyone gets to play more than once overall, but each part is taken as a stage, and that stage is basically a single act game. Now, feedback form basically says that there are a couple of rules to be followed. Those rules basically say the one who is starting should be able to tell what was the conclusion of the previous stage. So, for example, in this example, this is a multi-act game. Player 1 is playing twice, here and here. That's when the stage is changing. Player 2 is only playing once, so okay. Next, feedback form. This is also an example of feedback form because player 2 is starting, player 1 is starting the next stage and he knows the conclusion of the previous game, and he's actually starting at only one of those nodes. He's not starting at all of them. And that information is not lost anywhere further on. So this is feedback form also. What about this one? Is it multi-act? Is it feedback form? This next example. This is multi-act because players are getting to play in each stage. They're getting to play exactly once. That's not an issue. It's for it to be feedback form, here there should be singletons. That is true. And even further along the game, knowledge of which was the conclusion of the previous stage should be known to each player at all times. That is not satisfied over here. If instead of here the information set was, for example, here or here or even here, like within that one, then it was okay. Right now it's not feedback form, but it's still multi-act.
Right, makes sense.
Yeah. Okay. So then, okay, week 9 is behavioral strategies. Now let's talk about randomizing over these, randomizing in these extensive form games. So randomization can be done in two ways. Just like the solution concepts were of two kind, which was either in normal form or sorry, either in normal form or what we have as recursive rationality or by induction. Similarly, here we can have randomization at each information set. Yeah, meaning, for example, if this is what we had. Okay, now player 1 is only playing once, so there's nothing for player 1 to do. There are two strategies. He plays that, he can randomize on top of that. Sorted. That's a simple randomization. There's nothing there. For player 2, he's playing at two different nodes. That means his set of strategies are the Cartesian product of all of them. So Cartesian product of L2 R2 and L2 R2 dash. For him, the mixed strategies and behavioral strategies have different meaning. So mixed strategy basically means he will assign probability to each of these. This is a pure strategy now. This is a pure strategy in terms of normal form, right? So for this he'll assign a probability, for this he'll assign a probability, and so on. So he'll assign a probability in a way to this both combination. So what to do here and what to do here, what to do here and what to do here, that combination is what he's assigning probability to, and hence he has ultimately three parameters, three free parameters. The fourth one is sort of dependent, so we don't have to worry about it. The other kind of randomization is if he's doing randomization here and here at each node. That means he'll give a probability for this arm and this arm, versus he'll give a probability for this arm and this arm, not some coupling. This was a kind of a coupling. So that means for player 2 he'll have, let's say, probability beta here, and hence some beta 1 here, hence 1 minus beta 1 here, here some beta 2, and here with some probability 1 minus beta 2. That means there are two parameters. So remember, directly we can't have a relation between mixed and pure mixed and behavioral strategies. Reason being, the number of parameters are something that doesn't match. So one can't be a subset of the other if we can't even say that in terms of parameters. But we can still have a kind of an equivalence, and that equivalence is in terms of probabilities. So at each node or each vertex in the graph, if the probability of reaching that node, if he plays some behavioral strategy, if he plays some mixed strategy, is equal to the probability of reaching that same node if he were to play some behavioral strategy, given the others play whatever they want. If that probability is made equal, then we say that there is an equivalence. Now, is that equivalence always possible? Can mixed strategies, can there be a situation where there is a mixed strategy but there is no behavioral strategy, and vice versa? So we saw that this is also something that is captured in some definition called perfect recall. This perfect recall basically says, in simpler words, it just says that players are not absent-minded and they are not forgetful of what actions they took. They have not forgotten that they have even taken an action. 2, they remember what action they took, even if they're playing more than once. If they're playing once, that is easy. If they're playing more than once, then they should remember what action they took in the history. That should not be forgotten at any point of time further on. If that much is satisfied, that is what is called as perfect recall. So if there is perfect call, then it will give new strategy. And we said was that
What is the mention of one of the mixed strategy as a mixed strategy or vice versa? That was
there are relations. This is first. What was that instant every little strategy of play has an equivalent mixed strategy. This is part 1 of it. Part 2 is the following. It says that a behavior aspect he has, then every mixed strategy is equal to a behavioral strategy. In the case, what we need was if a player has recall, then for n2 nodes in the same instance we have the set distance actions are being exact same. So they're taking it everyone is being exact, and because of that they have a mixed strategy. So if every You can say that the study is to every this is the definition of innovation to but doesn't it need to be classified. Okay, so this covers with me. Okay, it's okay. So after that we saw the game where players are not part of the game there. All these through uh, diagrams similar to form. Then this is one possible way of looking at it. So this is saying there is some nature, some chance that is who choose which direction to go, but one knows what is he knows what type of the game it is, whether it's this one or this one. But player two does not know that, and hence for him all of these are part of one information set, and he can't distinguish between what is the type of the game. These two are just like that. So this is complete information. There are some players who will not know what is the game, what is the exact and this game. So there is only to look for to behavior. So in the what you required to do is this is step by step what you're supposed to. This is any level and something that very fine. So what it is. Be right and probability carefully. That's the first. If you make assign these probabilities, the problem is ready. Be careful. This so many that has one. But player one has two types. For player two, this we can like it. So player one can distinguish between its type, meaning player one, this one the probability to be different. We are writing about strategies. These are behavioral strategies. And so it's at this node that we are writing. This is the other diagram. This is exactly. It's you can think of it as this one. Player one acted first. He knows what is the type of the game. So for him, he has these actions, instructions, and he's going to be here. So he has two probabilities. So this is fine. Then two does the right thing. So he will LRR, and he can't decide which node of the he's at. Is the LRR, and what will be the probability of going here or here is captured by Q. So in these type of games, what you try to do is you should first start by a scenario which is the player who cannot distinguish between the information sets or cannot distinguish between the types. That player you can pick on the strategy, meaning you're actually reducing the game significantly. So you take Q to 0. That means you're focusing on this portion and this portion. Then for that, what is the best response? If Q is picked, what's the best response for player 1? And whatever response is that something that strategy becomes that whole strategy. Is that best response Q to 1 okay, if Q equal to 1 you fixed, and that tells you that okay U1 is the best response here, and whatever D2 is the best response here. Then what you need to check is if player 1 were to play 1 D2, is the best response of that for player 2. If that's true, then that already becomes a natural behavior. If not, you should look at the scenario also, which is of Q0 or rather Q equal to 1. Look at it and it tells you whether you get something from best, you some sort of a way of this value Q equal to 0. You should look at player 2's payoff for each of these values, and you try this way as we were going in mystery, so you will split them, and hence you will relation between these, so some relation between x and y. So that will limit what are the valid values. And for those valid values, is there any Q that is by default a best response for that region? If there is, that's the answer. If there isn't, then a range of Q will be the optimal answer, and all of those, whatever that range turns out to be for x, y, and q, that feeble range will be the Bayesian areas of the game that happened. Okay, so is combination games and how you're supposed to solve for them. Okay, I have covered up till week 10. Week 11, if you remember, was basically okay, one thing I'm going to call that. Question 7.
The column player has strategies and eliminating one of them so that
okay. Exact question I you already got you want TD max you have gotten, so that will be easier. And then you're supposed to what are you doing with the maximum limit, one of them. So for example, these two are by default eliminated because this is dominated by this is choice.
questions we'll choose the one that failed. The ground.
If you are there to calculate, there is this one another left. And then you can accept the other minimum. So check very maximum and this is one. That's why we can solve it. That's what's not. And the other minimum. You're pressing and then in section where you have this maximum thing, so I am discussing on this if you're not sure. Try out this thing if you're stuck in that again. I can go to these steps in class. This was for the I am not taking the recap. That's a theoretical factual type of a tutorial. So if you want, you can just skim through the notes, and that will be a quick revision of that topic. Okay, any further doubts? Anything else that you want clarified? Okay,
Can you like, sorry, I know that it's overtime, but if you have time, then once if you look at the questions two of assignment six.
question 2 of assignment 6. Okay, let me stop sharing the screen because it's not needed anymore.
Like,
Can you repeat which week did you say? Week 2 or week 6?
week six question
6. Okay.
This is something theoretical concept. Okay.
Okay.
So the answer to this is B, but I was also shouldn't C also, so shouldn't A also be the answer?
It's written in a slightly tricky way.